This is the fourth and final section of Chapter 6 Game Theory, and this section is all about converting games to linear programming problems. Now, before you watch this video, I would recommend that you are familiar with the simplex method, and I've got a video on that, and there should be a link above here, and you can click on that and you can watch that video first, because if you're familiar with the simplex method and how to use that as a method to solving linear programming problems, that would be helpful. So let's go through the steps to convert a game into a linear programming problem. Well, the first thing that we need to do is to make every element in the payoff matrix greater than 0 by adding n to every element. So let's say that we have a payoff matrix and the lowest value in that payoff matrix, let's say, was -5, that was the lowest value. We would add 6 to every element in the payoff matrix. We call that transforming the matrix, to ensure that every element is greater than 0. So not equal to 0, but greater than 0. We want all the elements to be positive. The next thing we need to do is to define our decision variables. So first decision variables that we are going to define are probabilities. So for example, P sub 1, P1 would be the probability of A playing row 1, P2 the probability of A playing row 2, and P3 probability of A playing row 3, and so on. We then need to say that each of these probabilities need to be greater than equal to 0. We then need to work out the value of the game to A. Now little v here would be the original value of the game to A. That's the original payoff matrix, but remember we added n to every element, so big V is going to be like the original payoff matrix plus n, this number that we added to make all the elements positive to transform the matrix. So big V is the transformed matrix value. And the last thing that we need to do is we need to say that we want to maximize the profit. We want to maximize A's payoff, and we do that by saying we're going to maximize P, and that is equal to V, the value to A in the transformed payoff matrix. Now these decision variables are going to be subject to some constraints. So we may have a constraint written down something like this: 3P1 plus 3P2 plus 3P3 is greater than or equal to V. And I'll show you how to do that in examples where these numbers come from. And we'd rearrange it, so we'd bring everything to one side, so we've got that constraint less than or equal to 0. So V minus 3P1, that's just been taken across, minus 2P2 minus 3P3 is less than or equal to 0. Now, if you need to write a linear programming problem for player B, from player B's perspective, then what we need to do, the original payoff matrix, we're going to transpose the matrix. That means we're going to interchange the rows and columns, and we also need to reverse the signs of each element in the matrix. So positives will become negatives, negatives will become positives, and then we do that first, and then we carry out the steps above here as before. And lastly, if you need to complete a initial simplex tableau from your inequalities, then some small changes will need to be made from those inequalities. But if you have watched the video on the simplex method, you will know all about this and why you need to do them. So I'm not going to go through it here, but I will just assume that you know what to do when we get to that part of the examples. Example 12. Alf and Bert play a zero-sum game represented by this payoff matrix below, which is here. And in part A, we need to formulate the game above as a linear programming problem for player A, writing the constraints as equations and defining your variables clearly. Well, the first thing that we need to do is we need to ensure that none of the values in the payoff matrix are negative. So we're going to add a value n to each one of them. Now the lowest value is -6, so if I add 7 to every element, it means that every element in that matrix now is going to be greater than 0. So let's do that. I've just shortened A plays 1 to A1 and B plays 2 to B2 and so on. So adding 7 to every element. So starting with the first one, we're going to add negative 2 plus 7, so we'll have 5, 4 plus 7, 11, 2 plus 7, 9, 0 plus 7, 7, negative 3 plus 7, 4, negative 2 plus 7, 5, negative 6 plus 7, 1. So the lowest element that you have in that original matrix should always become 1. And then we'll move on, 1 plus 7, 8, and then 3 plus 7, 10. So there should be no negative numbers or no zeros in this transformed matrix. It should be that the lowest value in that matrix is 1. Then you know that you've done it correctly. Obviously, be careful with your basic maths, just adding a value to each of those elements. The next thing we're going to do is assign a probability that A plays each row. And if A plays row 1, we're going to assign a probability of P1. That's not P to the power 1, it's P1. If A plays row 2, the probability they play row 2 is P2, and the probability that A plays row 3 is going to be P3. Now we need to write that down. Now I could write down a big long sentence. The probability that A plays row 1 is P1, the probability that A plays row 2 is P2, and so on, but we can write that in a nice short way. And what we can do, we can say this: let P1, P2 and P3 be the probabilities that A plays rows 1, 2 and 3 respectively. So respectively just means that probability P1 goes with row 1, P2 with row 2 and P3 with row 3. Now the original value of the game to A we're going to call little v, but we added 7 to that to get the new value of the game, which we'll call big V. So I'll just write down here that the value of the original game, or actually I'll just say let v, little v, equal the value of the original game to A. And I can then state that big V is equal to little v plus 7. So V basically represents the value of the new game to A. And with a linear programming problem, we either want to maximize P or minimize P. We want to maximize P, don't we? We want to maximize the amount that player A gets. And P is equal to V. P is equal to V, the value of the game. And that's what we want to maximize. But we use the letter P when we're talking about linear programming. Now this needs to be subject to some constraints, which we'll write down now. And what I'm going to do is I'm going to write it in a long way to start with, and then after that I'll show you the shorter way to write the answer down. So for example, if player B plays 1, they play column 1, the value of the game to A is going to be this. And we'll just go down the column. So 5P1, 5 times P1, so 5P1 plus 7P2 plus 7P2 plus 1P3 or plus P3 plus P3, and that needs to be greater than or equal to V. And in this form, it's always going to be greater than or equal to 3. Now, in a linear programming problem, we don't want it written in this form. It needs to be some sort of expression on this side less than or equal to 0. So if we rearrange it, what we'll get is V minus 5P1 minus 7P2 minus P3 is less than or equal to 0. So this is the form that we want. And actually we can go straight to this format. We don't need to write all of this out. If player B plays 1, the value of the game to A. This is what we finally want. So let's do that for the next two and go straight to what the solution is going to be. So let's think about it first. The next one, if B plays 2, the value of the game to A will be 11p1 plus 4p2 plus 8p3 is greater than or equal to V. So when we rearrange that, we'll have V minus 11p1 minus 4p2 minus 8p3 is less than or equal to 0. You can write out in the form, this form first if you prefer, and then rearrange it, or you can just do it in your head. It's simple enough. And then the last one, if B plays 3, the value of the game to A will be 9p1 plus 5p2 plus 10p3 is greater than or equal to V. And if we rearrange that, that will be V minus 9p1 minus 5p2 minus 10p3 is less than or equal to 0. Now the last thing that we need to do is we need to say that we want the sum of our probabilities less than or equal to 1. I know we want them equal to 1, but this is a linear programming problem, so we want this in this form. And then we've got non-negativity constraint, which means that all the variables that we've defined so far need to be non-negative. So we'll say V, that's the value of the game. That was a variable that we defined. The other variables that we defined were P1, P2 and P3. We need to state that all of these have to be non-negative, in other words greater than or equal to 0. Now if you're doing a question like this, the minimum that you need, you don't need to write everything that I've written down here, but we need to write down the first sentence that I've got here. So what the probabilities are of A playing a particular row, that's definitely needed. The next thing that you definitely need is to say that you want to maximize P, and that will be equal to V. V is going to be the value of the new game to A. You don't necessarily need to state that, but you do need to say that you're going to be maximizing P equal to V. And then the other thing that you need to say, it's going to be subject to some constraints, so subject to, and then we're going to have our inequalities here, 3 of them because we have 3 rows, and also our probabilities, we want them less than or equal to 1, and then we need to say that the variables that we've defined need to be greater than or equal to 0. So everything that I've highlighted in orange is the minimum that you need to write down if you are answering a question like this. Part B, write down initial simplex tableau for this problem. Now before we do that, our inequalities here need to be changed slightly to make sure they're in the right form for a simplex tableau. I know that there's going to be 1 or 2 headings that I can write down, so I know that I'll write down what my basic variables are here. That always goes in the first column. The value is going to be here. Hopefully this table is going to be big enough, but let's change our inequalities first. Okay, so what I'm going to do is highlight the bits that we need for part B. I'll just rub out the bits from part A for now. We don't need those, just to make it clear what we need to write down. And I've highlighted them also in orange. Right, so for part B, we want to state that we want to maximize P is equal to V, and it's going to be subject to some constraints. And as I said before, these constraints just need slight adjustment to make sure they're ready for the simplex tableau. The first thing is that our inequalities here need to be equal to 0, and to allow that to happen we need to add a slack variable. So let's do that to our first 3 inequalities. Now normally we start with the letter R in the alphabet, S, T, U and so on. So if we add R, S and T, we can now make these equal to 0. And because we want our probabilities here, we want this inequality written as equal to 1, we're going to add a slack variable, could be a surplus variable, just the next letter in the alphabet plus u is going to be equal to 1. And then lastly, I just need to add these variables to my list of non-negative ones here. So I've now got R, S, T and U, and I want those greater than or equal to 0. So now I'm ready to fill in the simplex tableau. So we have R, S, T, U and P as our basic variables. The variables that we have in our equations are V, P1, P2, P3, R, S, T and U, and all you need to do is to go through each equation and write down the coefficients of each one in the table. So if we start with the first one, we have V, 1V, we have minus 5P1, so minus 5, negative 5, negative 7P2, negative P3, so just negative 1, we've got an R, no S, no T, no U, and its value is 0 because it's equal to 0. Second equation here, we've got V, we've got negative 11P1s, negative 4P2, negative 8P3, we've got no R, we've got 1S, no T or U, and its value is 0. Third equation here, we've got a V1, we have negative 9P1, negative 5P2, negative 10P3, we have no R or S, we have a T, no U, and that value is also equal to 0. And then we have our probabilities here with our slack variable. So we have no V, but we've got a P1, a P2 and a P3, no R, S or T. There's a U, and the value of this one is equal to 1. Now for our last row of the simplex tableau, we're going to refer back to this statement here that we want to maximize P equals V. Now I just want to make it clear that this P down here is not P for probability. That's a big letter P, P for the profit. Now this objective function also needs to be written in this format, equal to 0. So I can rearrange it and say, well, actually what I want to do is to maximize P minus V is equal to 0. It's an equivalent to saying that P is equal to V. So that gives me the coefficient for V in this row of the table for the profit, and that's going to be negative 1. And there are no other letters in that constraint there, or the objective function, so everything else is 0. So that's where the negative 1 comes from in that last row. And pretty much all the problems you're going to do, if it's maximize P minus V, when you rearrange it, is always going to be that V has got a coefficient of negative 1. Now we don't need to actually use the simplex method, we just need to fill in this tableau. So we can now move on to part C, and part C says outline how you would change the method to formulate the game as a linear programming problem for player B. You do not need to formulate the problem. Now all we need to do is to transform the original payoff matrix so it's from B's perspective, and then we would carry on exactly as we did before. So to transpose the matrix so it's from B's perspective, we need to transpose the matrix so every row becomes a column, and we also need to reverse the signs of the numbers in the matrix. So I'll do each step one at a time. So the first column becomes the first row. So negative 2, 0, negative 6. The second column becomes the second row. So that would be 4, negative 3, 1. And then the third column now becomes the third row. So that's going to be 2, negative 2, 3. So that's step 1. Step 2 is that we need to reverse the signs of every element in the matrix. So all the positives are going to become negatives and all the negatives positive. So the -2 is now going to become a +2. The 4 and the minus becomes -4, and then the 2 becomes a -2. Second column, 0, that's going to stay the same. The -3 and -2 become positive, and in the last column the -6 becomes positive, and then the 1 and the 3 become negative. And then once we've done that, we would carry on as before. Now the question is not asking us to do it, but I'm just going to show you what would happen if we did carry on and started to form this as a linear programming problem for player B. So just like before, we would need to add a value n to each of these elements to make them all greater than 0. The lowest value is -4, so I'm going to now add 4 to each one of these values. So let's do that in a different color. So the 2 is now going to become a 6. Sorry, we're adding 5, aren't we, to every value? Actually, it might make sense if I don't try and do it all in the same matrix. Let's draw one underneath and put down here that we're going to be adding 5. Okay, so first one will be 7, not 6, and then 5, 11, 1, 8, 4, 3, 7, 2. Then from here we would say that we're going to maximize P equals V, where V is the value of the game to B, value of game to B. So all of this is optional when I ask for this, but just to show you what all of this is going to look like, we would assign a probability to each row, P1, P2, P3, and then we can write our inequalities down. So we would have 7P1 plus P2 plus P3 is greater than or equal to V, and so on. So you can see it's exactly the same as what we did before. Transpose the original matrix and reverse the signs, and then carry on exactly the same steps as previously. Example 13. Jenny and Mary play a zero-sum game represented by the payoff matrix for Jenny as shown below. You see it here. Convert the game into a linear programming problem for Jenny. Defining your decision variables, you should write the constraints as equations. Okay, so the first thing we need to do is to transform this matrix. So the lowest value is -3, so I'm going to add 4 to every element. So 1, 4, 6, 2, 6, 5, 4, 1, 2. So we'll start by saying that we're going to let P1, P2 and P3 be the probabilities that Jenny plays rows 1, 2 and 3 respectively. Now little v is going to be the value of the original game to Jenny. So the value of this new game to Jenny is big V is equal to little v plus 4. So let v equal the value of the game or the new game to Jenny, and we want to maximize P, which is going to be equal to V. Now before we write the constraints as equations, we're going to write them as inequalities. The equations are needed for the simplex method and for the tableau. We're going to write them as inequalities, and then we'll change them after that to equations. So the objective function is going to be subject to. So if I start here, let's write down, so this is P1, P2, P3. If Mary plays row 1, the value to Jenny is going to be P1 plus 2P2 plus 4P3 is greater than or equal to V. Remember that we need to write that so it's less than or equal to 0. I'm going to change them in a moment. So let's do this in blue because these are going to be changed. So it would be v minus p1 minus 2p2 minus 4p3 is less than or equal to 0. Then for if Mary plays 2v minus 4p1 minus 6p2 minus p3 is less than or equal to 0. And if Mary plays column, did I say row a minute ago? I meant column. If Mary plays column 3, that will be minus 6p1 minus 5p2 minus 2p3 is less than or equal to 0. Now we want the sum of our probabilities to add up to 1. So I could put equal to 1, but because I'm going to be using the simplex algorithm, that needs to be written as less than or equal to 1. Now I'm ready to convert these to equations. So these inequalities I need to add a slack variable. Let's do it in a different colour. So R, S, T and U. And I can now write for the first ones that they're going to be equal to 0 rather than less than or equal to 0. And the last one is going to be equal to 1. And I just need to state that I want all of my variables to be non-negative. So P1, P2, P3, R, S, T and U all need to be greater than or equal to 0. So these are my equations that I've got written here. I'm not going to change them to black. I'll just highlight them. So I'll just highlight what my final solution will be for this, that we need to maximize P equal to V subject to these constraints here, and also these variables being positive. Part B, write down an initial simplex tableau making your variables clear. Well, thankfully I have an empty tableau here in which I can put down my basic variables, which are going to be R, S, T, U and P for my profit, which I'm trying to maximize. And the variables that I have are V, P1, P2, P3, R, S, T and U, and I'll write down what their value is here. So we can go through each of the equations and then fill in this table. Right, so let's start with the first one. So I've got a V, a negative P1, a negative 2p2, a negative 4p3, an R, no S, T or U, and its value is 0. Second equation here, I have a V1, a minus 4p1, minus 6p2, and minus 1p3, no R, there's an S, and its value is 0. Third equation here, I have a V, negative 6p1, negative 5p2, negative 2p3, no R, S, there is a T, and again its value is 0. And for the probabilities here, no V, I've got a P1, P2, P3 and a U, whoops, a U, not a T, and its value is 1. And remember, maximizing P equals V is the same as maximizing P minus V is equal to 0. We always need to write that as an equation as well. So just write that down, maximize P minus V equals 0 in that form, which means that the coefficient of V is negative 1, as it will always be, and then all of these others here are 0. Part C. Using the simplex algorithm, the solution is obtained. P1 is equal to 0, P2 is equal to 3/7 and P3 is equal to 4/7. Find the value of the game to Jenny. Now, to find the value of the game to Jenny, we need to go back to the original inequalities that we wrote down for the linear programming problem, not the inequalities that we've got here for the simplex method. Now, if you remember, I'll write those down. Those were, and I can get those from the matrix here, payoff matrix, P1 plus 2P2, going down the first column, plus 4P3, sorry, that should be P2 there. And remember that the way that it's written is that those are greater than or equal to V. For the second column, 4P1 plus 6P2 plus P3 is greater than or equal to V. And 6P1 plus 5P2 plus 2P3 is greater than or equal to V. So let's substitute these values for P1, P2 and P3 into each of these equalities and see what we get. So if I start with the first value, so if I substitute 0 for P1, 3/7 for P2 and 4/7 for P3, that will give me 22/7. So 22/7 is greater than or equal to V. Now I'm just going to flip that around so that is V is less than or equal to 22/7. So just flip it around, it's going to be easier to work out. So V is less than or equal to 22/7. I'll do the same for the next one. V is going to be less than or equal to, so we'll replace P1 with 0, so we've got 4 times by 0, plus 6 times by 3/7, plus 4, just 4/7, and that will also give me a value of 22/7, so V's got to be less than 22/7. Then the last one, 6 times by 0, plus 5 times by 3/7, plus 2 times by 4/7 will give me a value of 23/7. Check that on your calculator. Now we want a value that satisfies all of these inequalities, and 23/7 does not satisfy the first two. So it's like the maxi-min, isn't it? Which is going to be 22/7. So the maximum of the minimums that satisfies all three is when V is equal to 22/7. Now this is the value of the transformed game to Jenny. We want to find the value of the original game, so we need to subtract 4 from this value. Remember we said up here, if basically this value here is 22/7 and the value of the original game plus 4 is 22/7, so the value of the original game V is going to be 22/7 minus 4, and that gives us a value of -6/7. So let's just highlight that, a bit difficult to see. So that would be your answer for part C. So don't forget that you need to subtract what you added to transform the payoff matrix if you want to find the value of the original game. So we've worked out what probability Jenny should play each game with, and we've also worked out what the value of that game is. We want to minimize her losses. So you should now be able to do exercise 6D on pages 207 to 209.